presentation. So looks like we're making that transition. If you will stand by, and you'll have Michelle with you here just shortly.
Okay, thank you, buddy. And I lost my dashboard, so I'm going to do this and see if that will work. Okay. Okay, thank you, buddy. And thank you, everyone, for sticking with us on this rest of the presentation. The rest of the presentation will be emphasizing the AWC standard of special design provisions for wind and seismic. And my portion of the presentation, I'll be covering the shear wall portion, and then Buddy will end up with the diaphragm portion. But I believe Buddy mentioned this before, then if you did download a PDF of the presentation, which I believe Brian and Marcy have been giving you the link to in the chat box, you can get a free download, a read-only version of the wind and seismic provisions, and it does include commentary, as Buddy mentioned. Also, on our website, if you are looking at our website and looking at our standards, there's an icon on our website that says what's changed. Now that is a really good link if you're interested in understanding and reading a white paper on what has changed from the previous version to the new version. And anyway, some tips on navigating around our website and finding some information. Now, as I mentioned, I'm going to be talking about wood frame shear walls, and we'll start with some videos and get into some basic information related to the wind and seismic provisions, and perhaps get into, well, we will get into some background behind some of the provisions that are in the wind and seismic provisions related to testing and the performance of wood shear walls that we've seen. And we'll get into a little bit of some design calculations as well. So what we'll talk about is, again, as Betty mentioned, we'll be talking about the seismic provisions, and we'll talk about the elements of the shear wall, also related to strength and stiffness, what provides that strength and stiffness of the shear wall, and some detailings and limitations when we're designing these types of shear walls using the wind and seismic provisions. So basic things that you'll get out of the standards and testing background regarding these standards. Now, before I jump into the actual document of wind and seismic provisions, I just want to step back and show a few videos. Oh, there's the details and limitations, but show you a few videos to get your mind thinking about the construction and what goes into a wood building. This video, which is available on YouTube, is about a project under the Neeswood House project, a two-story that was built via the University of Buffalo. And this video will show you a construction of the building that's a time lapse of over about 3 days. So let me go to the next slide, and hopefully you can see this. Okay. Then I'll start this. And unfortunately there is no sound because it won't go through the system. But as you can see, right now they're building the walls, and this is just to let those of you see who have never seen a building constructed or are not familiar with wood frame construction, to give you an idea of all the elements that are consisted of a wood building. You're seeing the floor diaphragm now being built. And then the second floor walls going up. You see OSB is the sheathing on the walls. And then a metal plate connected trusses that'll be erected. I'm sure if there's some builders in the audience, they wish all their projects went up this fast. Okay, that's great. So that gives you an idea of a building being constructed. The overall footprint of the building, let me get this, oops, wrong, I didn't want to start that. But the overall footprint, let me go back. The overall footprint of the building is 20 by 55 and it's 60 feet high. So, so that was built over 3 days. And the purpose of this actual structure was to actually test what finishes, for example, gypsum wallboard on the interior and stucco on the exterior, what contribution those materials or those finishes have to the overall performance of the building. And what I want to show you here is the project was actually tested once without any of the finish, just to get to understand how the building's going to perform. And then after it was tested a few more times with the finishes in place to see what contributions those finishes have to the performance of the building. Now, one thing I would like you to pay attention to is this area right here. And maybe I should, let me get my mouse. Where we have a wide opening, perhaps that's a garage door opening or a slider, and we have narrow shear walls on either side of those openings. So I'm going to run another video that shows you actually the test that was done. And let's see, I'm not getting that. Let me get this. Some reason okay, my computer just froze. Let me go back. Okay, let me go back. Okay, here. Let me just click on this one. Okay, for some reason that one video isn't working, so let me, and my computer is kind of freezing up now. Okay, if it doesn't work on the next one, sorry about this, folks. Please stay with us. And, uh-oh, it says restart program. Let me just wait for the program to respond. We are experiencing technical difficulties. Well, what you would see is the building would shake on the shaker table, and oh, let's see, cannot download, so let me go to the next one. Okay, let's see if this one, this is another view. The bottom photo shows you that opening with a narrow shear wall on either side of the opening, and it's looking down at that shear wall. So we have different views. And let me go to the next slide. Okay, let's see if this will work. We tested this before and the videos were working. Okay, it appears that the videos aren't working, which is unfortunate, but I'll give you the background behind it. The building did shake. It was tested without the finishes and then with the finishes, and they tested it to the 2,500-year event, a maximum credible earthquake, similar to what Buddy had mentioned previously on other tests. And what they found is that, in fact, yes, after it was tested, it did perform better, and in fact, it performed with improved performance, meaning that the drift limits were met, and the contribution of those finishes did help that performance. You know, we always say, oh, well, the finishes are going to help it perform better, but until you test it, it's not going to be, you're not going to be able to really provide factual information on that. But there is better controlled performance at those narrow panels as well, and and it also showed that it exhibited shear behavior, which was evident. You couldn't see it because it wasn't in the video, which was evident with the diagonal cracking of the stucco in that area. But the one thing also I wanted to point out is, even though it was shaken 3 to 4 times, there was some lengthening of the period as a result of that, but due to the multiple loadings. But still, it had a roughly period of 0.2 to 0.3 seconds period, which is what we see, what we expect from ASCE, and that's what ASCE standards are based off of, which are straight from ASCE 7. Now, so it was predicted to perform that way. They tested it. It did perform as it was predicted. And it's unfortunate that the video didn't work. But moving on. Now, this is the basic shear wall. And just going over the overall elements of the shear wall so we understand a little bit background on the shear wall when we're talking about it. What you see here is the brown portion of the figure. It represents the sheathing, the wood structural panels, and which are a specific grade and thickness, and also the white dots are the nails. Now the panels and the nails, these are critical to the strength and stiffness of the shear wall. That's what provides it. Then below that we have the framing, whatever we have them at studs at 16 inches on center or 24 inches on center. Per the wind and seismic provisions, that's the maximum you can have your stud spaced at, is at 24 inches on center. And then on either end of the shear wall, either end of the shear wall, there's my mouse, we have the boundary members, which can be typically either double studs or you have posts at each end. That resists your flexure in your shear wall. Then at the bottom of the shear wall, we have the sill plate, and therefore the panels are connected to the studs and the boundary members, and then they're also connected to the sill plate, which then eventually transfers the load to the anchor bolts that transfer the load to the foundation. And then also at each end of the shear wall we have the hold downs. That resists the overturning, the tension, and then the boundary members also resist the compression because you're going to have that overturning. Right here, so if you're looking at this, the shear load is going to the right. You would have compression on this boundary member and then tension on this boundary member. So that gives you the whole basics regarding shear walls. Now imagine this. If you have a building, imagine this is an 8x8 panel, and the 8x8 panel has nails at 6 inches on center. Well, you would have roughly 64 nails in that shear wall. Or even if it was at 2 inches on center, then you'd have 160 nails. Then imagine that you would have hundreds of feet of this. Say you have a 1,200 square foot house. If you extrapolate that, the nails of your shear walls, and then nails in your diaphragm, you could have 10,000 nails in your walls and floors and roof. Now this is an important thing to remember because the nails and the sheathing provide the ductility to your building, and we'll look at that in a minute. So something to think of. That's what provides the ductility in a wood system, in a wood building. Now the other thing to be aware of is when we go further into the presentation, based on history, based on testing, there are some failure areas in shear walls that we have found. One area is this area where we have two panels coming together on one member. So we have one panel here, a 4x8 panel here, a 4x8 panel here. And at this adjoining panel edge, which is the vocabulary or what we mentioned in the wind and seismic provision, this is an area where there could be some issues. And we'll look at how the wind and seismic provisions address those issues. Also, an area where we've seen some challenges or issues is at the sill plate, where we have some uplift on that sill plate. And we'll look at that also on some testing that is done, some specific detailing requirements, so that we can mitigate any brittle failures at this area in the sill plate. Okay, so that was a lot to go over. Now we'll get into a little bit more. Now I mentioned when we talked about ductility, we want to provide ductility in our system. So what does that mean, ductility? What does it mean to be a very strong shear wall? Well, when we design, whatever we do, we design our shear walls, we design our connections in our buildings, we want to have a good balance between strength and ductility. If we have a really strong wall, however, with no ductility, we would have very strong, and then it would fail abruptly, which is something that we don't want. We want to have some resiliency, or not resiliency, we want to have some ductility into that system so that it will go beyond that high strength and still not fail. That's very important. Now, also, in our systems, we don't want to have a lot of high ductility because it could be so flexible and so ductile that it can't provide any strength to the system. So what we want to do is provide a very good balance between the two. And that there. So we want to provide good strength and good ductility, providing that balance. So shifting gears, and many of you, if you've seen past AWC presentations, you'll get a kick out of this session, or maybe you're rolling your eyes, oh, not again, but whatever the case may be. Just to give you a visual of a better, not thinking as an engineer, but as a, you can say a kid, what does it mean to be ductile and what does it mean to be brittle? Well, brittle could be similar to peanut brittle. And, for example, peanut brittle is very strong, but if you bite on it or hammer it, it will crack right away. And that's something we want. It's very abrupt. There's no indication that it's going to fail. It just cracks. Now, taffy, on the other hand, this is something that's very fluid. It moves, yet it doesn't hold much strength because it's just going to move. Now, what the question is of the day, this is a big question, is which type of candy would you choose as a very good balance between ductile and brittle? So we got O. Henry, we've got Big Cherry, and we've got Butterfinger, we've got Big Hunk, Snickers, or Payday. Now that I've been speaking or presenting around the country, I realize that the people on the East Coast, unfortunately, probably, well, you may never have heard of Big Hunk, so I'll have to come up with another version. But I was thinking a good balance between ductility and strength is Big Hunk. And it has, if you're not familiar with Big Hunk, it's fluid, flexible, but it's also got a lot of strength. So anyway, on the feedback survey, you can comment and say you didn't like this section, or you can even recommend a different candy for the East Coast that people on the East Coast would be familiar with. Anyway, so now seriously, getting back into the shear wall and all what we're trying to accomplish here and learning about stiffness and strength and what that all means to a shear wall. Here's some test results from an 8x8 wood structural panel that was tested using Puree protocol and cyclic testing. And as you can see, through different through the application of load cyclically applied, we see that when the load is applied, it displaces. So we have on the horizontal axis displacement, 3 inches, 1, 2, 3, and 4 inches. And then on the vertical axis is is the applied load. So what we see here is at 3 inches, this is where we met our displacement and our maximum load. That's the load where we had peak load at 3% at 3-inch displacement, which is a drift capacity of a 3%, which is very good. That's what we expect, and that's what we design, what we have determined from calculations is this 3% drift. And what we see here is along the lines of 1.5 inches, which is roughly actually around, is it 1.5 inches? Where we have, let's see, that's about over 10,000 right now. But around this location, this is where we actually design our shear walls, the strength that we design our shear walls. So it's 3 times less strength, and 3 times less the drift is around 1 inches. That's where we design. So now the other thing to view from this graph is that after we've exceeded this displacement and applied more strength, you can see that there was a failure. So it can't resist any more loads, and there was a failure here, and it goes beyond the 3 inches, but it's still holding in place. Now, the one thing to take away from this is that after is the ability of wood structural systems or wood structural panels the benefit of it is its ability to displace without failure, meaning it displaced 3 inches without failure. And even after peak load, it still displaced more, and there wasn't a whole lot of failure in the system. But what happened in this location where there was some failure, there was probably something, perhaps panel nailing, edging pulled out, or the nail pulled through the panel, or the withdrawal from the framing. Those are the failure mechanisms. Now let's look at some details on some of the failure mechanisms. Here on the left, we see where the nail pulled, nail yielded at the adjoining panel edges, and we'll talk more about this detailing, but you can see there's 2 tube-eyes, and at this, where the panel joints occurred, they were nailed off to these 2 tube-eyes, but you can see it yielded, nail yielding here at these adjoining panel edges. The other picture on the right is at the sill plate where you see nail yielding. There was the head of the nail pulled through at the bottom of the panel location here. You can see there's no nail. So the other important thing is that this was a ductile failure where we had the nail yielding, and this is what we want. We want a ductile failure. We don't want the sill plate breaking or other types of failure. The wood structural panel breaking. We don't want any of that. We want this nail yielding because that's what provides the ductility of our system. Okay, now that we've seen some testing and we've seen some results of testing and some failures, now we'll get into the practical application where we're getting into the wind and seismic provisions. But then, before we get into that, I jumped ahead too soon, we have a poll.
All right, sorry about that. Let me launch that. Here we go. What are the 5 parts of a wood shear wall? All right, we've got A, WSP, nails, wood frame, hold downs, and top plates. B, WSP, nails, floor diaphragm, hold downs, and plate anchors. C, WSP, nails, wood frame, staples, and plate anchors. Or D, WSP, nails, wood frame, hold downs, and plate anchors.
And WSP stands for wood structural panels.
Sorry, thank you.
Oh, that's okay. They probably got it.
It's a close race between A and D at this point. People are voting, so. All right, I've got about 65% of you have voted. I'm going to close it at 70. All right, here we go. And let's see, 69% say D, wood structural panels, nails, wood frame, hold downs, and plate anchors, and 25% say A. And I guess the difference there is top plates instead of plate anchors. So, all right, Michelle, what is the real answer?
Okay, the real answer that we have is wood structural panels, nails, wood framing, hold-downs, and plate anchors. However, it seems like the top plates actually should be part of the shear wall as well. So maybe Buddy and I can discuss this. We'll debate this at the end on what the actual correct answer should be. But for now, let's hold that thought. And I'm sure we're going to get a lot of comments on this. But we'll move forward. And then we can bring it up later in the presentation. So we'll keep you in suspense on the, and you guys can debate it if you're with other people on what you